Hello ladies and gentlemen, I am Desi Marantika from Faculty of Engineering, University of Indonesia. Thank you for the opportunity letting me to speak in 4th International Research Conference on Applied Science and Engineering Technology and 7th International Conference on Social Science, Humanities and Technology 2023. Today I will present my study about system dynamics modeling, the impact of fare adjustment and service improvement policies to public service obligation subsidies on Jabodetabek Commuterline. Indonesia has a metropolitan area around the capital city of Jakarta, which is called Jabodetabek, Jakarta, Bogor, Depok, Tangerang, and Bekasi. Jakarta, as the center of government and economy in Indonesia, requires a buffer city around it as a unit because the population density in Jakarta is already very high. The buffer city is the home base for workers in Jakarta. Therefore, the Jabodetabek area is filled with commuters who commute daily to work in Jakarta. In order to support the movement of commuters, an efficient public transportation system is needed. There are several types of public transportation such as Commuterline, bus rapid transit, and light rapid transit that serve the Jabodetabek area. Commuterline is the largest mode of mass transportation in Jabodetabek. The Jabodetabek Commuterline consists of 5 lines with 7 connections covering a service distance of 418.5 kilometers and has 81 stations. Based on the data from Kereta Api Indonesia Commuter as an operator, the number of the Jabodetabek Commuter Line's passenger averaged 800,000 people per day on weekdays and 700,000 people per day on weekends on January 2023. Before the COVID-19 pandemic occurred, the average number of Jabodetabek Commuter Line's passenger reached 1.2 million people per day. The Jabodetabek Commuter Line is one of the modes of transportation in Indonesia which receives subsidies from the government in the form of a public service obligation or PSO. Public service obligation is a form of subsidy that is currently developing in the Indonesian transportation sector. In general, PSO is a cost that must be incurred by the state due to the disparity in the cost of products or services sold by a business entity with prices for certain products or services set by the government, so that products or services are guaranteed and affordable for most of society. The Jabodetabek Commuter Line's fare since 2016 until now is 3,000 Indonesian rupiah for the first 25 kilometers and 1,000 Indonesian rupiah for every additional 10 kilometers that follows. The fare is a commercial rate set by the government. Meanwhile, the fare calculated by the operator is 6,250 Indonesian rupiah for the first 25 kilometers and 2,500 Indonesian rupiah for each additional 10 kilometers that follows. This difference in fare then becomes a PSO subsidy from the government. The number of PSO subsidies for the Jabodetabek Commuter Line continues to grow every year. In 2016, it was about 1.1 trillion, while in 2021, it was about 1.6 trillion Indonesian rupiah. This is in line with the increasing number of passengers and effort to improve services. Because the PSO subsidies are given to all passengers in the form of a fare differences so that the fare paid by passengers remains reasonable. As the number of passengers increases, the PSO subsidy that must be given will also increase. Currently, the amount of the PSO subsidies for the Jabodetabek Commuter Line is too much of a burden on state finance. The principle of providing subsidies that are right on target needs to be maintained so that social inequality does not occur. Therefore, it is necessary to study the PSO subsidy scheme for the Jabodetabek Commuter Line currently used in order to obtain a more effective scheme or policy from the perspective of the government, business entities, the Jabodetabek Commuter Line's users, and the wider community. This research will focus more on knowing the effect of implementing fare adjustment and service improvement policies on Jabodetabek Commuter Line's PSO subsidies. System dynamics is a methodology based on feedback systems taken from control theory and can be used to solve non-linearity problems, time delays, and multi-loop structures of complex and dynamic systems. In general, the stages of modeling using a dynamic system can be seen in the following diagram. I will immediately discuss the explanation of the stages in the next chapter, that is model development. This study uses dynamic system modeling, which requires two types of data, namely mental data and numerical data. Both data can be obtained from interview, field observation, or literature reviews. Historical data used in data from 2013 until 2022, while model simulation are carried out until 2050. Okay, first step of system dynamics modeling is problem definition. This research started with concerns that the amount of PSO subsidies for the Jabodetabek commuter line continues to increase even though the number of passengers has also increased. The value of the subsidies is too burdensome to state finance, so it is necessary to review the existing subsidy scheme. The purpose of this study is to find out how the effect of implementing fare adjustment and service improvement policies on PSO subsidies on Jabodetabek commuter line. After determining the problem definition, the next step is to develop a theory called the dynamic hypothesis, which consists of research hypothesis, global models, and the concept of causal loop diagram. The hypothesis of this research is that the population in Jabodetabek will continue to grow, so that the need for public transportation will continue to increase. Along with the increase in demand, it is also necessary to improve services so that the passenger can be served properly. Service improvement will certainly increase operational and maintenance costs, so the fare will be more expensive. If there is no fare adjustment over time, the subsidy will increase. While adjusting fares can reduce subsidies, it can also reduce demand. The second step is making conceptual model. The global model based on the problem in this study can be seen in the following diagram. At the stage of developing the global model, the role of each stakeholder involved in the problem is identified. In this case, the stakeholders involved are broadly divided into three, namely passengers, operators, and regulators. After the global model is complete, the next step is to create a causal loop diagram. Causal loop diagram is a tool to represent global models and then develop based on the mental data that has been collected so that it can be the basis for building models. CLD consists of the variables connected by arrows indicating causal influence between these variables. A positive arrow indicates that the causal relationship between variables is unidirectional or mutually reinforcing. For example, the relationship between level of service and willingness to pay. The higher the Jabodetabek commuter line service level, the greater the willingness of people to pay the fare, so that the willingness to pay value will be greater. Conversely, an arrow with a negative sign indicates that the two variables are mutually opposite or the causal relationship is mutually weakening. For example, the relationship between published fare and potential demand. This means that the greater the fare that needs to be paid by passengers or published fare will reduce the amount of potential demand. After causal loop diagram is formed, the next step is to create a system dynamics model using stock and flow diagrams. To facilitate model development, this study is divided into several submodels. First, submodel population and GRDP. This submodel discusses the relationship between Jabodetabek GRDP and Jabodetabek population. Historical data of GRDP and population were obtained from the Indonesian Central Bureau of Statistics, which were then subjected to regression analysis so that the elasticity of GRDP to population was 0.22. This means that every 1% increase in GRDP will increase the population by 0.22%. The second submodel indicated travel demand. Submodel ability to pay and willingness to pay. Next, submodel demand passengers. Next, submodel investment, operation, and maintenance costs. Next, submodel revenue. Revenue is income received by the operator for the business results of providing transportation services. Next, submodel fare, real cost, and amount of subsidy. Next, submodel BSO subsidies. Calculation of the amount of BSO subsidies can be done using two approaches, namely fare subsidies and cash flow gap subsidies. Fare subsidies is the differences between real cost and published fare multiplied by passengers kilometers. Cash flow gap subsidies means the difference between IOM cost and revenue. Okay, now we move to the next stage. Model testing is carried out in several stages. After the model is complied, it is necessary to input data or parameters for each variable, so that the model can be run or verified. After running and successful, it means that the parameters and equations in the model are appropriate. The behavior test in this study was carried out on the population, GRDP, actual demand, car ownership, IOM cost, revenue variables. Based on the validation of the behavior test on the 6 variables, the result is that the behavior of all these variables resembles the actual conditions shown by the overlapping of the simulation result graphs with historical data graphs. Even if there is a deviation, the value is not too big. Thus, the model created and the parameters entered can be used to describe the BSO subsidy calculation system in Jabodetabek Commuterline. The next is final model testing. To find out how the effect of fare adjustment and service improvements on the Jabodetabek Commuterline BSO subsidies, the following policy scenario is created. Business as usual conditions indicate that the model will run as usual under current conditions without any changes. The current fare, which is 3,000 Indonesian rupiah for the first 25 kilometers or 120 per kilometer, will be left intact until 20 and 50. Service levels will also be left as they are today. In scenario 1, a change in fare setting policy was made, which was previously based on government policy to be determined based on ability to pay, willingness to pay, and real cost. When the real cost is greater than the average ability and willingness to pay, then the fare is in accordance with the average ability and willingness to pay value and vice versa. Scenarios 2, 3, 4, and 5 carried out service improvement by looking at the load factor. When the load factor at peak hours exceeds the limit, services are gradually increased, including increasing the number of train trips at peak hours, reducing headway, and increasing the number of carriages. The next chapter is result and discussion. After running all scenarios, the result is the published fare per passenger for the first 25 km will continue to increase in the scenario that applies the fare adjustment policy. Whereas in business as usual conditions and scenario 2, where fare adjustments are not carried out, the published fare will remain at 3,000 Indonesian rupiah per 25 kilometers until 2050. The largest increase in value occurs in scenario 5, where fares are determined by only the value of ability to pay, willingness to pay, and real cost, and are carried out service improvement when load factor exceeds 100%. Even though the number of passengers are also increased, the real costs generated are still greater. So, the published fare is also high. Based on the result of running all scenarios, the result is that the increase in the values of BSO subsidies drastically occurs in scenario 2, 3, and 4. Meanwhile, under business as usual conditions, the increase is not dramatic due to the absence of service improvement that can increase IOM costs. In scenario 1, subsidies are no longer needed since 2030 because there are no service improvement but there are fare adjustments. However, scenario 1 cannot be implemented because service facilities will experience depreciation over time and the population will continue to increase, so then the number of demands will continue to increase. If there are no service improvements at all, the Jabodetabek commuter line will no longer be able to serve passengers optimally. Based on this result, it can be concluded that the most optimal scenario for reducing PSO subsidies in Jabodetabek commuter line with fare adjustment and service improvement policies is scenario 5. This is because in 2029 to 2044, in this scenario, the PSO subsidy value is zero. This means that the income earned by operator is greater than the IOM cost that needs to be spent. Even though in 2045 to 2050 subsidies will be needed again, the value will not be as big as the other scenarios. The fare adjustment and service improvement policies can reduce PSO subsidies with a published rate below the ability to pay value and increasing demand. Here are some references that I used in this study. Well, that's my presentation regarding the result of my study. I hope this study can become input for stakeholders related to Jabodetabek commuter line and be useful for everyone. Last but not least, I would like to apologize if there are some mistakes in this presentation and thank to all parties who have helped me complete this study. If there is anything that needs to be discussed, please contact me via this email. Thank you and have a nice day.